This lecture will go through a model updating case study so you can see some of the physics, some of the phenomena that we see when we try to update models. And we'll also talk about how to find the design sensitivities in Nastran by using scripting from MATLAB. We've talked about before the fact that a complicated structure such as NASA's Space Launch System is composed of lots of different parts, and a lot of the uncertainties in the model come in the joints between the parts. And so those are often some of the variables that are being updated, the stiffnesses in bolted joints. For example, in SLS, there are bolts between flange joints with bolts possibly between a lot of these different sections. There are kind of pin type joints that hold the solid rocket boosters onto the core stage, and those are frangible joints where you can blow those off and the boosters will fall away. Similarly with some of the shells that can pop off and once you get into space to allow the vehicle to go free. And then you have other joints like in the solid rocket boosters themselves, we have a steel case and then the propellant, which is more of a rubbery material, kind of pressed into that steel case. And so there might be some uncertainty in how those two bond together, for example. So anyway, those are all the types of joints that you might be updating. In this case study, we're going to look only at just two bolted joints. So we have a really simple structure here. It's two beams. There's a cutout here so they can't slap together when they bend. And then there's a bolted joint on each end. And there aren't really any good methods yet that exist for predicting the stiffness and damping of a joint like this. And usually we don't want a lot of density in the finite element model, so we don't want to model this in a lot of detail. So what's done in this case study is the usual approach where we, instead of modeling that bolt, we just take all of the nodes at the two surfaces, we spider them down to a single point, and then we connect those 2 points with springs that will represent the stiffness of the bolt. And so there are actually 6 spring constants. We can have motion in all the 3 translational directions, and then we can have rotational motion about all the different axes of that joint. What we also did here, that's also typical in a case like this, is we've actually used a Hurdy-Craig-Bampton model to reduce this structure down just to the interface degrees of freedom. So we keep 6 degrees of freedom for this node, 6 for that node, a few fixed interface modes, and the same thing on the other side. That makes a really small, really compact model so that we can quickly iterate and try a lot of different values for the stiffness to find the one that matches the best. So as you can see here, a test was performed. So in this test, we measured the mode shapes and natural frequencies of some of the low-order modes of this structure. So we know what the natural frequencies should be. We have this model, and our main uncertainties are just the stiffnesses of these joints. So we'll use model updating to try to determine what those should be so that our finite element model becomes a good approximation for this. And if we were back to the NASA system, what we would be doing is then using that finite element model to do predictions of flight, dynamics during flight or loads during flight. So that would be the purpose of the model updating. Okay, so now we're ready to start. As background, these are the main modes that were measured. So we have various different kinds of motion. The beams are kind of opening up and clapping in this mode. In the second mode, they're kind of bending in unison. And you can imagine these are going to stress the joints differently. This one wants to open and close, so like the axial stiffness in the bolt along the z direction might be really important there. This one the beams want to shear the joint, so it's mostly X direction stiffness that might matter, right? Because the red beam has a longer distance to go to bend the same amount as the green, and so it's going to put a stress in that lateral direction there. And you could go through and you could think through all of these modes and the different types of things that might matter. So that might give us some clues. So the first thing we did here in this study was to run a bunch of analyses. Because this model was cheap, we had the luxury of running the model many times with lots of different values for the different parameters. For a complicated model, you might not be able to do this. So we have the Young's modulus of the two beams as one parameter, and it's pretty straightforward. These lines show the errors in each of the different natural frequencies, modes 1 through 6. So the error in the finite element model relative to measurements as we vary the parameter. And so we see that we can change any of the natural frequencies by changing the Young's modulus, and we only have to change it a little bit to get them to agree with the model. Unfortunately, we can't fix the whole problem that way because all of the frequencies change in unison. So for example, if we pick a frequency that has this red line, mode 2, at 0 error, we'll have the purple line, mode 4, at about 2.5% error. So, so we have to make a trade-off, or we have to find some other variable that we can change that will allow us to dial this all in. By the way, these are small errors here. If this was SLS, you'd probably be happy and go home by the time you got all the errors under 2 or 3%. But this is a super simple structure, right? I mean, we should be able to do pretty well. We should be able to say nail this. So as we ran the spider plot analysis, though, on all the other spring constants, and notice we go through many orders of magnitude. We don't have any really good way of knowing what those stiffnesses are. We could come up with some back of the envelope estimates for some of them, but it's tricky to know, so we just ran them through many orders of magnitude. And I wanted to point out one really important feature that, for example, this X direction spring doesn't really affect any of the modes. The only one it affects is mode 2. And that makes sense if you think about the physics that I explained a minute ago. All of these other modes are completely independent of that. But notice that there's also this interesting phenomenon where if that spring is stiff enough, it no longer changes mode 2 at all. And so we have to get kind of into this golden region for this to have effect. And that's a frequent occurrence. Often you need to dial springs, way up or way down to kind of find that region where they really have an effect. If you were to start, say, a gradient-based optimizer in this point, it's gonna tell you that mode 2 is completely insensitive to that spring, and it's not going to try to change it at all. And you'll just be stuck because notice that none of the other springs affect that mode either. So, but if we decrease it, we find there's a region right about here where a certain value of kx will give us, bring mode 2 into perfect agreement with the measurements. And we go through and we see similar things on the other modes. Mode 6 is dependent on ky, but also really dependent on the rotational spring in the z direction. This is like a torsion mode, so it makes sense that torquing on this part here would be important. And this y direction spring is important for, let's see, that's modes 5 and mode 1. So anyway, you can kind of use this picture and actually just kind of pick points off the graphs and figure out what all of the different spring constants should be. And so you don't really even need to now run some fancy gradient-based optimizer. You can just kind of read them off the plot. Now you might run into some contradictions. For example, mode 6 wants ky to be, to be a certain value to for it to come into agreement. But then, that same value of ky, well, let's see, that's not a good example. But there can be examples of parameters where you make a change, for example, if we, actually, no, I guess there aren't really any good examples of that here. Maybe the one that we could point out is that, if we choose a value of krz to optimize this plot here, mode 6, we get certain errors in mode 4 and mode 5. And so we'd have to find some other parameter that we can vary to take care of those. And you can come into a case where you still can't satisfy all the criteria you want to simultaneously. All right, so anyway, that's that case study. You can see kind of how we come up with stiffnesses. This shows you what we were able to achieve, the different natural frequencies and then the errors in the natural frequencies, using an optimization and using some good starting values from those plots. We also looked at various different kinds of spiders. So this connection could be a rigid connection. So basically this spider rigidizes this surface so it moves as a rigid body. Or there's RBE3 in Nastran, or an averaging type constraint that basically just allows these surfaces to remain free and uses all the displacements of all the nodes on these interfaces to estimate the average, to kind of average and estimate the displacement that this point would have if it was tied to all of those points in an average sense. We also looked at a big area and a small area. And anyway, depending on which approach we used, we could get different results. And, in some cases, we got very good results for all the natural frequencies, all under 1%. Notice, though, there's this mode 4 that there was nothing we could do to bring that one into agreement. And if you look back at the picture, that's bending in the stiff direction. And so none of those springs is going to change that. The only thing that can affect mode 4 is changing Young's modulus. But if we choose a Young's modulus that brings it into agreement, we can mess up the others. So we had to just accept that error. We had also actually done a test on a single beam that was uncoupled from any others, and we knew that the Young's modulus we had was the right value for the structure, so we didn't want to go change it and mess that up. So basically our model's probably just missing the parameter that we need to get that mode to dial in. So we were looking at some other things here, some of which aren't really relevant to this class, but rather than go into that, I will mention that we were interested in this model in using a nonlinear element to capture both frequency and damping in the joint. So the frequencies that you saw weren't the only criteria we were trying to capture. And one thing we found as we were trying to do that is that if we would plot on one side the error in the frequency and the error in damping on another axis, and then we tried lots and lots of different models with lots of different sets of parameters, we would eventually observe this Pareto Front. And basically this is a region where no parameter can cause an improvement of the model, can cause the model to improve any further. So in this, with one of this shape, we're basically stuck with choosing either a low error in frequency right here, or a low error in damping over here, or we can take some compromise. So here are some examples. So this is damping and frequency. So this point over here has a really low error in frequency and a really low error in damping and a high error in frequency. Over here we have the opposite case, right? And then if we take some point in the middle, we can maybe find a compromise. But these types of Pareto fronts often appear, and they basically tell us that the model isn't capable, we're missing some parameter, and so the model isn't capable of capturing what we want it to capture. In this case, we had the luxury of digging a little farther and looking for a new parameter that we could vary. And we basically saw that as we, this is a three-dimensional plot, so we're varying the parameter by going upward, and we saw that we could change the shape of that Pareto front by varying this parameter. And eventually we could find a solution that came down here and had both low frequency and damping error. I guess there's still kind of a Pareto front, but we've moved it much lower. So this kind of thing can happen when you do model updating, and it's part of why it's an art and part of why it's still challenging. Okay, so we've already covered that. I want to show you one other thing, and that's an example of how you can calculate Jacobians and also create things like these spider plots using MATLAB. For example, well, even in these spider plot cases, right? I mean, you can tell I've run probably 20 different cases to construct this curve, right? Run the model 20 different times. It would be a lot of work to type into Nastran 20 different values for kx and run all of these and load them in. You definitely could do that, but it's not fun. So this example will show you a faster way to do this, where you can basically have MATLAB automatically run all of those different cases. Now there are, in terms of the design sensitivity matrix, there are some even better approaches, and we'll talk about that at the end, but this is a good approach for what we want to do. Okay, so let's switch over to MATLAB, and we'll look at how we can do this. This is basically a script, and it's going to call Nastran. This right here is a call to Nastran. Basically, we're doing a DOS command Nastran and give it the name of my model so that it will actually run that model. So we're going to have MATLAB call Nastran, and after it's done, read in the natural frequencies that Nastran spits out, and then we're going to change something in the model and rerun it. So for this to work, we need a couple things. We're going to be changing things in the BLK file, the bulk file. So I made two copies of it. I made a master copy that I'm not going to change, and a copy called temp that I will change. And that's important because we might mess something up. I'm going to use a little MATLAB script called replace in file that you need to download off the course website and make sure it's on your path. And it's going to do kind of the hard work. And then we'll go from there. I did also want to mention that this kind of approach is common. I used something like this at Sandia. There they had a very powerful tool called a prepro. And it's basically like this, a replace in file function where you could, it's maybe farther in here where you can actually see this, but you prepare your text file with some special delimiters, and it would automatically replace values within those delimiters with whatever you wanted. So if you're in a Linux environment, this is great. There might be Windows versions of this. But this replace in file is a really easy MATLAB way to do it. Okay, so how does this work? First of all, what do we have to prepare? So I prepared a folder. So I downloaded from Nastran all the files, and I put them in a separate folder so that I can change things and not worry about messing up the originals. And basically, the DAT files are exactly as they were before. This is our favorite 44 node beam. The only thing I'll change is that these two DAT files point to different bulk files. So depending on which case I want to run, I change the bulk file I'm pointing to. So so there's the one that I would run. This one is exactly the same, but I gave it a different name so that when I run it in Nastran, the files will be saved with a different name. I probably didn't really need to do that. Okay, so I have those, and then within the bulk file, I have to find the value I want to change. So if we look through this file, here are all the different grid points, the different elements, and finally down here we find a definition for the p-bar elements, and we have the area, the inertia properties. I want to change this first inertia, I1. But notice if I use the standard Nastran format, I only have a couple of digits to work with. And so it's hard to apply a small perturbation to that parameter. So what I did is I switched to the Nastran 16 character rather than 8 character format. And so here it allows you to break lines. So the first line just has these values. And then we follow with a second line where I can put the rest of them. And then I did one other thing. I added 2 zeros to the value so that now if I do a search within this file, there's only one occurrence of that value. So I can tell replace in file to find this string and to replace it with whatever I want, and it won't disrupt. It won't find anything else and make any other replacements that I don't want it to. Now notice I probably could have added a couple more zeros if I want to, really have high accuracy. I'm not quite at my 16 character limit, but this is good enough for what I'm going to do. Okay, so and we could change other parameters too, the torsion, the mass, any of the other parameters could be changed in a similar way. Okay, so there's that file. So how do we do this in MATLAB? All I do is I run the model once to get the original natural frequencies. And then I want to change the parameter by 5%. So if I multiply these numbers together in the command window, that tells me that this is the new value I want. And if I wanted to really be positive that I haven't rounded off any digits, I could change to long format and see that, yes, that truly is the value I want. It only has those digits. So to replace that in the file, all I do is I give this function the old value, the new value, and then I give it the name of the file that it's going to go do the replacement in. And it does its magic, and now I have a new version of beam44 temp that will include the updated parameter. So now I call Nastran again. This time I run b44 temp p so that I don't corrupt my previous F06 file. And it calls this, this updated bulk file. And when it's done, I have the results in an F06 file. Oh, by the way, I don't think I need these pause statements the way that MATLAB actually runs. Okay, so then what I do is I save a copy of that F06 file for later, just in case I want it. So I call it P05 since I did a 5% increase. And now I've read in the natural frequencies, I can calculate the Jacobian as the difference of those divided by the change in the parameter. And let's take it that far and let's get it started running. So if I hit run, it echoes out to me the information it got from the operating system as it's running Nastran. It ran once, it ran twice. Now it's running this last time. So let's look back at what we got. So it gave us some information. It said it's starting the job, it finished it. Then reading in the frequencies, these are the natural frequencies that we got. Let's see, or actually I guess I didn't echo out the original ones. These are the perturbed natural frequencies. There's a Jacobian I calculated. By the way, this replace in file function, it's kind of handy. It actually spits out a message that says this is the line that I used to do the replacement. And it'll give you a message if it throws an error. So, so it ran those 2 times, it calculates the Jacobian, and then just to test this out, I also ran it with a 10% change. So that, to do that, I'm changing the value to 2.387. So I ran one more time, and then what I did is I used the Jacobian to try to calculate what that frequency should have been. So this final table, and I'll make that a little more readable. This final table has the original natural frequencies. It has those that are the true ones that I calculate from Nastran, perturbing the inertia property 10%. And then it has the estimate I get from the Jacobian. So if I take the Jacobian times 0.1, that's the linear Jacobian estimate of what these frequencies should be. And you can see that it gets really pretty close for almost all of those frequencies. So it's done a good job. It's able to estimate most of those frequencies accurately. We can see that a little better if we make a bar plot. I'll have to maybe zoom in on just a couple cases to really see this. But for each of these modes, what you see in the blue is the original natural frequency. The red is the true perturbed value, and the yellow is the perturbed value I get from the Jacobian. So notice some modes are more sensitive than others, though almost any mode is sensitive to a change in the inertia. And if we zoom in, we can kind of see, relative to the original value, how well our Jacobian is doing at estimating the perturbed values. So anyway, that's one way you can calculate a Jacobian. You could also write a for loop, and you could loop over lots of different values of the parameters. And you could calculate the natural frequency as a function of the stiffness and create the spider plots similar to what you saw here. And if your model's not too large, it won't take it very long at all to run through a calculation like that. So anyway, that's a simple way to get Jacobians in using MATLAB and using this kind of scripting. I'll just mention quickly there, is a more professional, more elegant way to do this. Nastran can do sensitivity analysis, and here's an example structure that you can find where it demos how to do this. This is a it's called general purpose satellite. It's basically made to be like a satellite, but it's not any real satellite, so nothing in it's proprietary or export controlled or anything. But basically you have all the pieces a real satellite would have. You have a main bus, you have a solar array, some antenna, and so the modes of this would be like the modes of a satellite. To be honest, I'm not sure if this is supposed to be a deployed or a stowed configuration. Looks kind of like it's deployed. But anyway, this could be a model updating problem where you'd have all kinds of different design variables, stiffnesses of some springs, Young's modulus of various different parts, shell thicknesses, all kinds of different parameters like that. And here there's a specify in like how large of a change you're going to allow in each of those variables, perhaps. So in this case, you might have some test natural frequencies for the satellite and your pretest model, and these two aren't in agreement. So we want to try to find a way to change all of these design variables such that we bring these modes into agreement. So you could calculate the design sensitivity matrix using that MATLAB approach I gave you. But this is going to be a lot of Nastran runs, right? I mean, there's lots of design parameters, design variables, and so you're going to have to run a lot of times to calculate finite different Jacobians. Nastran has an optimization capability built in, this solution 200. And so this gives you an idea of what a file might look like that runs that. I won't go through all the details. I will mention this example case study is one from the Attune updating package, and they actually have their own DMAP that takes the capability that's built into solution 200 and adds, additional instructions. With these DMAPs, you can change things at like the fundamental, like matrix multiplication, mass matrix, stiffness matrix multiplication level. So this is really handy and a powerful tool. And there are things that are done here that you couldn't do without that DMAP. But basically, the setup for the files is kind of like what I've already showed you. You would set your file up. A lot of these are the usual settings we're used to. And then somewhere you'd have your bulk data file where you have the parameters that might be varied. And then, there's some additional files. This is the specifications for the different design sensitivities that you want. There's one for material property data. And so these are all going to give instructions on how to do that. So just an example of the, how you specify design variables. So, you give them a name. We could use, different ways of defining them in Nastran. Notice it's using the 16 character setup. And then like an initial or nominal value. And, depending on the kind of parameter, you define them differently. But you can do different things, like you can set a whole bunch of parameters to be the same and vary them all together, or you can, have them be independent. So, and, once you've done all of that, Nastran will then have the intelligence it needs to go in and update the material properties. And with the help of the DMAP, it will actually calculate the design sensitivities. So you can read this from the Nastran manual and learn about, how the default Nastran design variable capability works. You'd have to go to the Attune help to see how their DMAP alter, what bells and whistles it adds and what additional instructions you have. So anyway, there's an example for an interesting and a very, realistic scale problem. And the files for this are up on the course website if you want to look at this in more detail. Though this gets into kind of a ninja level Nastran. So I expect that for the project, a lot of you might just use the simple approach, probably most of you. But if you do want to dive in and learn a little more Nastran, everything you need to do that is here. All right, so that concludes our lecture.